which is numbered as question 2, but here's the first question that we have, especially from the topic of momentum. So the first question says, in a safety test, a car of mass 1100 kilograms travel at a speed of 10 meter per second and collides with a stationary van of mass 3000. After the collision, the car and van move together with a velocity v. Okay, and then we have the diagram. Everything is given on the diagram as well. But for the first one, the total momentum of the car and the van is conserved during the collision. It's always conserved if there is no external force. This is the law of conservation of momentum. But in the first one, we need to define momentum. So momentum is defined as the product of mass and velocity. For definitions, we gotta be very precise. Product of mass and velocity. State the unit of momentum. The unit of momentum is kilogram meter per second, or you can write it this way, kgms minus 1. We can also write Newton second, but this one is also fine. Now the next one is calculate the velocity v of the car and the van after the collision. So before the collision, they were moving with the different velocities. After the collision, they join together, and we need to find the mass. We need to find the collective velocity after the collision. So what is the statement, or what is the expression that we use in this case? Well, we use the law of conservation of momentum, which is m1 u1 plus m2 u2 equals to m1 v1 plus m2 v2. This is a general expression. If the objects join after the collision, you can improvise the same expression. If objects join after the collision, if the objects have joined after the collision, the same expression can be improvised as m1 u1 plus m2 u2 equals to m1 plus m2 times v. Because if they join after the collision, they'll be moving at the same speed. That's why v is taken common on the right side. Now let us insert the values. Okay, I'll keep it very simple. I could have done it directly. I can find the momentum before collision within seconds, but I'll just keep it really simple. So I'll insert each and every value one by one. So m1 represents the mass of one of the object. We're going to call the mass of the car as m1 and mass of the van as m2. So I need to write m1 times u1 plus m2 times u2 equals to m1 plus m2 times v. So I've inserted the value just by looking at the diagram, and this is what we get. This is the expression that we get. Now we simply need to simplify this expression. So on the left side, I'll be getting 1 1 0 0. All of it would be reduced to 0 equals sorry 4100. Okay, 3000 plus 1100, 4100 times v. Now 4100 would be shifted on the other side. 11000 divided by 4100 equals to V, and we can find the value of V from here. Alright, in the next one, we need to find the total kinetic energy of the car and the van after the collision. For this one, I can write down, at least I can write down the formula, although this is not from the topic of momentum, but still we should be able to find this one as well. Kinetic energy equals to 1 over 2 mv square. So 1 over 2 as it is. We need to find the kinetic energy of the car and the van. Their collective mass is 4100 and their collective speed is 2.7 square of it. Then we write this thing as it is on the calculator. So 1 over 2 simply means 0.5 times 4100 times square of 2.1. On the calculator we get 14944. In 2SF I can simply write it as 15,000. If you want to copy paste the answer, you can. Totally your choice. Alright, so this is the next question that we have. A spare the mass of the spacecraft is 300 kilograms. It's moving in a straight line at a speed of 8,000 meter per second. So speed is also given 8,000 meter per second. In the first step, we need to find momentum. The formula of momentum is product of mass and velocity. Mass is given as 300. Velocity is given at 8,000. So 8 threes are 24 followed by 4 zeros. And another 0 followed by 5 zeros. Matter of fact. You can also write it this way: 2.4 into 10 raised power 1, 2, 3, 4, 5, 6 kilogram meter per second is the unit which is given already. So usually the trend is all the answers which are greater than 10,000, we usually write it this way in the powers of 10. Okay. So what was the case, by the way? The aircraft of mass this much, it was moving with the speed of, okay, so this is what we had initially. We had an aircraft. May not be a good drawing, but this is what it looked like. We had the aircraft. It was moving with the speed of how much? 800 meter per second initially. So this is what happens before. So what happens afterwards? The fuel on the aircraft explodes and the spacecraft splits into two parts. The direction in which the parts move does not change. Okay, the two parts move in the same direction. After the explosion, the speed of the front part increases to 9,000 meter per second. It has a mass of 150. Calculate the speed of the rear part of the after the explosion. So this is what happens before, and this is what happens afterwards. This aircraft is split into two parts. This is the first one. Let's say now this one has a mass of 150 kilograms. Initially the total mass was 300 kilograms. The first part is having a mass of 150. It's moving with a speed of 9,000 meter per second. Likewise, the second part, all right, it is also moving in the same direction. the leftover mass would be 150 kilograms because the total mass was 300. The first part is having the mass 150, so thereby the second part should also be having 150. And then we don't know the speed of it. That speed needs to be found out. So once again, we use the standard equation, which is the law of conservation of momentum, m1u1 plus m2u2 equals to m1v1 plus m2v2. On the left side, what do we have on the left side, by the way? On the left side, we have the momentum before the collision. In this case, before the explosion. And on the right side, we have the momentum after the explosion. Now, the thing is, do I need to insert the value of m1, u1, m2, u2? Matter of fact, we don't have two objects before the explosion. It was just a single object. And I don't need to insert the value of m1, u1. Matter of fact, I don't even have m2. It was just one piece before the explosion. But the thing is, whatever the momentum was, whatever the total momentum was before the explosion, we found that momentum already. It was 2.6 into 10 to the power 6. So on the left side, without inserting any value, I can simply write the momentum before the explosion, which is 2.4 into 10 to the power 6. So technically, before the explosion, the expression was simply m into v, because there was just a single mass and that was just moving with a single speed. So it would be even better that you write the expression, you improvise the expression. I'm not saying it's a new expression, it's the same expression, but you improvise the expression with something like this. I can write u here. U represents initial speed, equals to m1 v1 plus m2 v2. Let's say the aircraft was broken into 3 parts after the explosion. Now the new expression would have been improvised into something like this, m3 v3. So the momentum before the explosion was 2.4 into 10 to the power 6. Do we have the mass of the first part? Yes, 150. Do we have the speed of the first part? Yes, 9,000 plus m2. Do we have the mass of the second part? Yes, 150. Do we have the speed of the second part? No, we don't. So I'm going to write v2 as it is. In the next step, just calculation, just mathematics from here. I'm going to write this thing on the calculator. $150 times 9,000. You get 1, 3, 5, 4 zeros plus 150 v2. What do we do afterwards? 2.4 into 10 to the power 6 minus whatever our initial answer was. It gets 105 tetra 0. And on the right side, we are left with 150 v2. So I shifted this thing on the left side, and it was subtracted from 2.4 into 10 to the power 6. In the last step, I'm going to divide whatever my answer is with 150, and I get 7,000. meter per second. So 7,000 meter per second is the speed of the second part after the explosion. The total kinetic energy of the two parts after the explosion is greater than the original kinetic energy of this spacecraft. State the energy transfer that occurs in the explosion. Chemical potential energy of the fuel is transferred in form of kinetic energy after the explosion. The explosion lasts 0.20 seconds. Calculate the average resultant force on the front part during this time. So whenever they use the word average force, this is the expression that is used to calculate the resultant force. Wording wise, they would use the word calculate the resultant force. So you should be using the expression F resultant equals to ma. When they use this word calculate the average force, the chances are you have to use the expression delta P over delta T. Delta P represents the change in momentum, delta T is the time 0.20, but delta P represents the change in momentum. So what's the change in momentum? Well, all we need to find is the change in momentum. And we need to find the change in momentum of the first part during this time. So initially, when the first part was just joined with was just a single piece, the speed was 8,000. This is the initial speed. After that, the first part is having the speed 9,000. So delta P, the expression of delta P, the formula is m into v minus u. This is the formula of delta P. Delta P means change in momentum. You can write it this way, mv minus mu, which is then equal to m into v minus u. So what was the mass of the front part? Well, the mass of the front part was 150. What was the final speed? 9,000. What was the initial speed? 8,000 divided by what is the time of collision, or should I say the time of explosion? It is 0.20. So it should simply be 150 multiplied by 1,000. 150, 1 2 3 more zeros divided by what? Divided by 0.2. We get 75 tetra 0 into 10 raised power 5.